friends to a new session on genomics and proteomics. In this session, we will discuss proteomics, 2D gels ES and MALDI TOF MS antibody, applications and future prospects. Proteomics is a rapidly growing field of molecular biology that is concerned with the systematic, high throughput approach to a protein expression analysis of a cell or an organism. The cell responds to internal and external changes by regulating the activity and level of its protein. Therefore, changes in the proteome, that is a collection of all the proteins coded in our genes, provide a snapshot of the cell in action. Proteomics enables the understanding the structure, functions and interactions of the entire protein content in a specific organism. The term protein was introduced by the Swedish chemist Jöns Jacob Berzelius 1938, an accomplished experimenter in the field of electrochemistry. The first protein studies that can be called proteomics began in 1975 with the introduction of the two-dimensional gel and mapping of the proteins from Escherichia coli, guinea pig and mouse. The terms proteome and proteomics were coined in the early 1990s by Mark Wilkins, a student at Australia's Macquarie University, in order to mirror the terms genomics and genome. Today, many different areas of study are explored by proteomics. Amongst them are protein interaction studies, protein function, protein modifications and protein localization studies. Antibody based proteomics play a very important role in biomarker discovery and validation, facilitating the high throughput evaluation of candidate markers. Technologies such as 2D PAGE and MS are used to identify the main proteins found in a particular sample and proteins differentially expressed in related samples. Example, when comparing diseased and healthy tissue. Two-dimensional gel electrophoresis. Two-dimensional gel electrophoresis has been instrumental in the birth and developments of proteomics, although it is no longer the exclusive separation tool used in the field of proteomics. One of the first reports of successful two-dimensional electrophoresis coupling IEF, that is isoelectric focusing, to SDS PAGE sodium dodecyl sulfate polyacrylamide gel electrophoresis was published 1974, but unnoticed because of two features. The first one was the inclusion of the sample within the IEF tube gel, which is a quite efficient but slightly cumbersome process. The second was the detection method, that is the classical coercive blue staining in alcohol acid mixtures. However, a report by O'Farrell 1975 using a cathodic sample application and showing hundreds of distinct spots through the use of autoradiography of 35S labeled proteins was accepted. The resolution was much greater than with other two-dimensional techniques. Example, those using native IEF or those using another type of zone electrophoresis as the first dimension. However, two core features of these early days had very strong consequences. The first one is the rather poor reproducibility of IEF with carrier ampholites, which is prone to several problems such as cathodic drift. The second one was the absence of technique enabling to identify a specific protein spot on a 2D gel. These two major pitfalls were the subject of intense research that succeeded at the ends of 80s, on the one hand with the introduction of immobilized pH gradients and on the other hand with protein identification with advanced sequencing. With protein sequencing, it became possible to identify spots on 2D gels almost at will, although it was much more labor intensive and less sensitive with advanced sequencing that it is now with mass spectrometry, which also achieved a quantum leap in speed, sensitivity and depth of protein characterization after 2D electrophoresis. Basic concept. The basic concept of 2D electrophoresis is shown in figure 1. 2D electrophoresis suggests that it is two-step process. It is indeed a 5-step process. First, sample preparation prior to the first separation. Second, first separation. Third, interfacing with the second separation. Fourth, second separation, and fifth, protein detection. Generally, the order of separations is first IEF and second SDS electrophoresis. Both are very sensitive to the presence of ampholites and of non-ionic detergents, two types of chemicals that are almost indispensable in denaturing isoelectric focusing, but are limited to the buffer front when the classical order of separations is used. Sample preparation. As the first separation is almost isoelectric focusing, it brings two types of constraints. First of all, the charge of the proteins must not be altered in any way. A combination of shower drops and detergents is almost always used for this. Shower drops are excellent protein denaturing and solubilizing agents and neutral shower drops such as urea. However, shower drops alone are not sufficient as they do not dissolve cellular lipids efficiently and are not able to keep proteins soluble enough under the conditions prevailing in IEF. To achieve both purposes, electrically neutral detergents are always added during sample preparation. Any type of detergent completely neutral over the whole pH range of IEF and compatible with the shower drops can be used. Example, CHAPS 3,3-cholamidopropyl dimethyl ammonio 1-propane sulfate. The second important point that has profound consequences is that the fact that IEF operates at very high field strength due to the fact that the charge of the proteins continuously decreases. Thus, to make them travel very high electric fields, 170 volt per centimeter must be used in IEF compared to SDS electrophoresis 15 volt per centimeter. Finally, sample preparation concerns protein modification. These can be by chemical modification. Example, carbamylation induced by the presence of urea, and this is indeed more a problem during sample preparation and storage than during 2D electrophoresis itself. Isoelectric focusing. As IEF is a steady state technique, the sample can be theoretically applied at any point of the pH gradient without altering the final result. The sample is generally applied at one of the extremities of the pH gradient or dispersed with the IEF gel. In carrier ampholites based focusing, dispersion requires to include the sample in the gel during the polymerization of the gel itself. Voltage profile is a direct consequence of the high field strengths that must be used in IEF. Quite often, biological samples are not completely desalted and the salts present can induce a strong Joule heating if high field strength is applied at once. This is also true at a lesser extent for the ampholites that are used as conductivity smootheners, which must reach their isoelectric point. For both salts and ampholites, advantage is taken of their high mobility compared to proteins, and moderate field strength is used for some time, typically 15 volt per centimeter for 3 hours to allow them to reach their final position. Then the high field strength is applied. Equilibration between dimension and SDS electrophoresis. The purpose of the interdimension equilibration process is to coat the proteins separated in the IEF gel with SDS so that they become mobile in the second dimension. This is always achieved by equilibration of the IEF gel in a SDS containing buffer, but it has been shown to be more delicate for immobilized pH gradient strips due to electroendosmosis problems. Starts the SDS electrophoresis at low voltage just to give time to the SDS front to resolubilize the protein while sweeping across the immobilized pH gradient strip. Then SDS electrophoresis can be conducted the usual way. Protein detection and image analysis. 2D gel based proteomics is the only step in which there is an intermediate readout before the mass spectrometry stage. This step plays a crucial role as only what is detected can be further analyzed, and quantitative variations observed at this stage are the basis to select the few spots of interest in comparative studies that will be the only ones processed for further analysis with mass spectrometry. There are enormous constraints and demands on this protein detection step, such as sensitivity, linearity and homogeneity of response, as well as compatibility with downstream processes such as mass spectrometry. Current in gel protein detection methods fall into three major categories: detection with organic dyes, silver staining and fluorescence. Detection with organic dyes involves colloidal coercive blue staining, which has really become a reference standard. Although the sensitivity is moderate, linearity and homogeneity are good and compatibility with mass spectrometry is excellent. Conversely, silver staining is much more sensitive but less linear and homogeneous because of its delicate mechanism. Protein detection by fluorescence combines good sensitivity with excellent linearity and compatibility with mass spectrometry is good. In addition, several modes of detection can be used as reviewed: environment sensitive probes, non-covalent binding and covalent binding. The latter approach deserves some specific comments, as the use of the chemically related reactive fluorescent probes, differing mainly by their excitation and emission wavelengths, allows performing multiplexing of samples on 2D gels. However, it must be stressed that the image analysis process in 2D gel based proteomics is usually not the simple comparison of two gels, but the multiple comparison of several gel images. Current uses of 2D electrophoresis in proteomics. In 2D gel based proteomics, the 2D gel part represents the essential workload of the whole process. As it's this step that the quantitative analysis is performed, and this is usually used to perform spot selection. This has important consequences for the downstream mass spectrometry analysis. This means that only a very limited portion of the proteins present in the samples will need to be analyzed. This is especially true for a comparative study with replicates. If 10 samples to be analyzed and compared at 20 hours of mass spectrometry per sample, this represents in shotgun type techniques 200 hours of MS. If the same analysis is carried out with 2D gels, at the end of the image analysis, maybe 20 different spots will be selected, and this represents at the very most 20 hours of MS. When analyzing the comparative productivity of 2D gel based proteomics and shotgun type proteomics, it appears that the compared productivity of 2D gels over shotgun improves when the size of the sample series increases due to the highly parallel nature of 2D gel based proteomics. Future prospects. 2D electrophoresis is now a mature technique, and it offers great flexibility and tunable resolution, and many tricks are available to tune and refine the resolution when needed. There is therefore little gain to expect as to the pure performances of 2D gels by themselves. When keeping to fully denaturing 2D electrophoresis, several systems purely based on zone electrophoresis have been developed, mainly to alleviate the solubility problem encountered with the membrane proteins. While these systems did alleviate this specific problem, they never came to wide use because of their insufficient resolution, thereby offering no real advantage over their techniques based on 1D SDS page. Thus, progress in the optimal use of 2D gel based proteomics will come from two sides. The upstream side will be to use more and more 2D gels on cell fractions, and decisive progress will come when more robust fractionation techniques than the current ones will become available. The downstream side will be to use 2D gels where it brings most added value compared to other proteomics steps. One of these areas is clearly in the determination of post-translational modifications. Thus, the name of the game for proteomics in the future will be to determine the quantities and qualities of proteins. There will be, however, no match for proteomic techniques as far as post-translational modifications are concerned, and any tool that can be useful in this subfield of proteomics will prove useful for the future of proteomics. So, it is quite clear that 2D gel based proteomics will still be used in the 21st century proteomics. Matrix assisted laser desorption ionization time of flight mass spectrometry, or MALDI-TOF-MS. MALDI-TOF-MS has been applied for the analysis of a wide range of biomolecules. The term MALDI was coined in 1985 by Franz Hillenkamp, Michael Carras and co-workers. They found that the amino acid alanine could be ionized more easily if it was mixed with the amino acid tryptophan and irradiated with the pulsed 266 nanometer laser. The tryptophan was absorbing the laser energy and helping to ionize the non-absorbing alanine. Peptides up to the 2843 Dalton peptide melittin could be ionized when mixed with this kind of matrix. In MALDI, the sample is incorporated into matrix molecules and then subjected to irradiation by the laser. The laser promotes the formation of molecular ions. The matrix is typically a small energy absorbing molecule such as 2,5-dihydroxybenzoic acid or alpha cyano 4-hydroxycinnamic acid. The analyte is spotted along with the matrix on a metal plate and allowed to evaporate, resulting in the formation of crystals. The plate is then placed in the mass spectrometer and the laser is automatically targeted to a specific places on the plate. Since sample application can be performed by a robot, the entire process including data collection and analysis can be automated. This is the single biggest advantage of MALDI. Mass analysis follows the conversion of proteins or peptides to molecular ions. This is accomplished by the mass analyzers in the mass spectrometer, which resolves the molecular ions on the basis of their mass and charge in a vacuum. In MALDI-TOF, the ions termed in an ion source are accelerated in an electric field and thereafter propagate through the field-free region before reaching the detector. When entering the field-free region, all ions of the same charge state have obtained approximately the same kinetic energy, which is defined by the acceleration voltage. Hence, low mass ions will travel faster and hit the detector before heavier ions. A TOF spectrum is obtained by measuring the time elapsed from the laser pulse to the detection of the various ions having propagated through the field-free region and by measuring the intensity of the detector signal at each time. Summation of TOF spectrum from several laser shots is typically performed. A mass spectrum can be obtained by converting the TOF to mass by Z using the fundamental relations between these quantities via a calibration procedure. To improve resolution, MALDI-TOF instruments are often equipped with a delayed extraction facility. Reflector MALDI-TOF instruments are equipped with an electrostatic mirror to improve the resolution. MALDI-TOF MS has the advantage of showing all the under-methylated products which are insufficiently volatile to be observed by GC-MS analysis. MALDI techniques typically employ the use of UV lasers such as nitrogen lasers 337 nanometer and frequency tripled and quadrupled ND-YAG lasers 355 and 266 nanometer respectively. Although not as common, infrared lasers are used due to their softer mode of ionization. The laser is fired at the matrix crystals in the dry droplet spot. The matrix absorbs the laser energy and it is thought that primarily the matrix is dissolved and ionized by addition of a proton by this event. The matrix is then thought to transfer proton to the analyte molecules, example protein molecules, thus charging the analyte. Ions observed after this process consist of neutral molecule and an added or removed ion. Together they form a quasi-molecular ion, for example M plus H plus in the case of an added proton, M plus Na plus in the case of an added sodium ion, M minus H minus in the case of a removed proton. MALDI is capable of creating singly charged ions, but multiply the charged ions M plus NH and N plus can also be created as a function of the matrix, the laser intensity and or the voltage used. One of the challenges in the development of the therapeutic antibodies is the development of a fast and precise method to determine the molecular weight of antibodies. Historically, gel analysis, size exclusion, analytical ultracentrifugation and MALDI-TOF MS have been used to determine the molecular weight of their entire molecule or if its separate components. However, each of these methods suffers from either imprecise molecular weight determination or from the lengthy time required to perform the analysis. Mass spectrometry based approaches for targeted protein quantification are based on the concept of isotope dilution mass spectrometry techniques commonly used for the detection of small molecules. The approach is comparable to modern advanced antibody-based methods such as the multi-analyte profiling platform MAP, offering multiplexing detection capability with an excellent dynamic range. While the antibody development is central to the success of an ELISA-based platform, MS provides alternative and complementary approach which can precisely detect a wide variety of peptides or proteins via high mass accuracy and or peptide sequencing. This approach provides high selectivity and specificity and technically avoids most of the problems associated with optimization of multiple assays in a single measurement. The mass spectrometry based technique has a unique capability to perform candidate based proteome browsing and measure absolute levels of post-translational modifications, demonstrate the general components of mass spectrometry based approaches for targeted protein quantification. An antibody is a large Y-shaped protein used by the immune system to identify and neutralize foreign objects such as bacteria and viruses. Each antibody recognizes a unique antigen target. It consists of two identical light chains and two identical heavy chains held together by interchain disulfides and non-covalent interactions. Furthermore, post-translational modifications occur during cellular development and production, and these can affect the properties of the antibody. For example, if the amino terminus of the heavy chain starts with a glutamine residue, it can be converted to pyroglutamate. Also, on the heavy chains, the C-terminal residue is often a lysine residue that may be post-translationally excised. Of additional importance is the addition of various glycans to an asparagine residue in the heavy chain, generating an N-glycan linkage. MAP's entire modifications need to be characterized quickly and accurately as part of bioprocess development for the evaluation of product consistency. A critical component of characterization is an accurate determination of the antibody's molecular weight, which is important because the mass provides a glimpse of the integrity of the structure. Future prospects. The prospects of this technology are exciting and promising. It is a long journey to develop a robust, high-throughput multifunctional system that can provide sophisticated function that we desperately need in the clinical diagnosis and therapy. Most of the current spectrometry-based platform technologies require a combination of multiple sample preparations such as immunosubtraction, multidimensional LC separation, immunoaffinity and or solid phase extraction to enhance the analytical dynamic range and detection sensitivity. These requirements limit the capability for high throughput. Thus, the major caveat for the current mass spectrometry based approaches for targeted analysis is the lack of a high throughput pipeline integrating a highly specific and ideally single step sample preparation strategy. The development of a quantitative detection technology that provides high specificity and sensitivity, multiplexing, absolute quantification and PTM monitoring should provide us a powerful tool for a broad range of applications and greatly enhance our effort in developing better medicine. Let us summarize the following discussion on proteomics, 2D gels ES and MALDI TOF MS antibody applications and future prospects. Proteomics is a rapidly growing field of molecular biology that is concerned with the systematic high throughput approach to protein expression analysis of a cell or an organism. Proteomics enables the understanding of the structure, function and interactions of the entire protein content in a specific organism. Antibody-based proteomics play a very important role in biomarker discovery and validation, facilitating a high throughput evaluation of candidate markers. Technologies such as 2D PAGE and MS are used to identify the main proteins found in a particular sample and proteins differentially expressed in related samples. Two-dimensional gel electrophoresis has been instrumental in the birth and developments of proteomics, although it is no longer the exclusive separation tool used in the field of proteomics. Mass spectrometry based approaches for targeted protein quantification are based on the concept of isotope dilution mass spectrometry techniques commonly used for the detection of small molecules. Before we attend the next unit, please try to answer the following questions. Write an overview on proteomics. Discuss the equilibration between dimension and SDS electrophoresis. Write short note on 2D gel electrophoresis. Discuss the importance of isoelectric focusing and SDS in proteomics. Discuss how to prepare samples for 2D gel electrophoresis. Here are some references for you. Introduction to Bioinformatics, Atwood and Perry Smith, Pearson Education. Bioinformatics, a beginner's guide by Jean-Michel Claverie, John Wiley and Sons. Structural Bioinformatics by Philip E. Bourne and Helge Wilsling-Willey. Bioinformatics, Methods and Applications, Rastogi, S.C. Mentiretta N. and Rastogi P. Prentice Hall of India Private Limited, New Delhi. Hope this session was enriching for you. See you the next session. Till then, bye.